Hello and welcome to my Qubes OS Mini Summit 2021 talk, which will be about S-RTM and Secure Boot for VMs and current status of the development progress. My name is Piotr Król. I'm founder of 3M Dev and CEO of that company. I was contributor of Core Boot and maintainer. I co-organized and organized various conferences. I'm conference speaker. I train at various organizations, and I'm former Intel BIOS software engineer. I'm 12 years in business and probably for 5 or more years using Qubes OS. I'm also having C-level position in various organizations, which you can see logos of on this slide. So who's 3M Dev? What we're doing? We are a Core Boot licensed service provider since 2016 and participant of Core Boot leadership call. So what means that if you, for example, OEM and seeking for Qubes OS certification, then you will need open source firmware or at least some auditable firmware. And of course, with Core Boot, you can achieve that. So, for example, we supporting companies in getting through the certification of Qubes OS. Other thing that we're doing is UEFI adopting. We also develop UEFI as well as Core Boot. We are also Yocto participants and embedded Linux experts since 2019. What means we take care about firmware of embedded devices, IoT gateways, and similar stuff. We are also official consultants for Linux Foundation FWPD LVFS project, which is project which goal has to deliver firmware updates to Linux-based devices, which can be laptop and all the peripherals connected. So we support companies in enabling this updates delivery. We are also IBM Open Power Foundation members since 2020, and one of our engineers is a chair of Systems of Software Working Group since this year. So what we will talk about today, a little bit about presentation goal and terminology. What is S-RTM, S-RTM, how it function in our boot chain, and what happened over last year in S-RTM and Secure Boot technology. What are the key takeaways from the events and from the presentations from various meetings, and what kind of challenges this bring, so we can move forward to understand, so we can have one presentation which gathers all the information and move forward with development, having that summary. Finally, we will shift to Q&A. So the goal of this presentation is to discuss state of integration of various S-RTM and verified boot technologies for virtual machines. But this has some implications. There are some things that have to happen in order, because there are many topics involved. We need some checkpoints. We need some places where we can gather everything together and say, okay, this was done, this is in progress, this is what we have to do, and still we probably will make some decisions in the process. And of course, if we want to enable new developers in the ecosystem and move S-RTM and verified boot technologies forward, then of course it's good to have this presentation that gathers everything together. So this presentation is about gathering all this information, and to be honest, quite a lot happened over last year since my last presentation about this topic, and I hope this will be good resource to move the discussion forward. So let's start with terminology just to have common ground. Of course, I explained that in the past, but so what's S-RTM? S-RTM is a static root of trust for measurement. So in reality, this would be either something which is code or core root of trust for measurement, which is static. Static means static in time, not static by placing it in root-only memory. Of course, this happens often that the implementation is in that way, but still, the static means this is static point in time, typically at the beginning of the platform booting. So we have some root of trust, which gives us beginning of the word for measurements or for verification, depending on the needs. And this can be either implemented as a code, as some kind of a code, which I will tell you what kind of examples we have, or as a hardware. Secure Boot was used in the title of presentation just like more for marketing purpose, because Secure Boot as a term is technically imprecise. It does not explain what it really is. It is more complex situation. It typically consists of couple technologies, and when we're saying Secure Boot, we typically think UEFI Secure Boot, or maybe we talk about set of various technologies, which I will explain on further slides. So it's better to use verified boot terminology, which means, of course, that we verify every boot stage one after another, and this is more precise term. Depending on the situation, if root of trust is used for measurement and or verification, we should use other abbreviation, and this would be more precise, like secure static core root of trust for measurement, static core root of trust for verification, or maybe even some static core root of trust for measurement and verification. This would be more comprehensive statement. In terms of other terminology that I will use, system ROM, which will be on next slide, is a place where boot firmware is stored. Of course, ROM indicates read-only memory. It's not always like that. Very often it can be written because we have ability to deliver updates there. But let's say system ROM is a terminology that I use. In case of a boot process that I will present, it is based on platform initialization and unified extensible firmware interface specification, so PI and UEFI specification, which are maintained by UEFI forum. And according to the specification, we have following boot stages. Of course, there is more. They define more, but the important things for this presentations are SEC, which is security phase. This is first boot phase according to PI specification. It should be root of trust for the platform, but it's not always like that. There are things that can verify SEC phase. There is PEI phase, which is pre-FI initialization, which is kind of second stage, which prepare everything to start Dixie phase, which is driver execution environment. This stage typically detects hardware and apply correct drivers so this hardware can be used in the boot process. And finally, we have boot device selection, and boot device selection is okay, like finally we discovered all the hardware during boot process, and then we're looking for okay, which device we're booting from. Is this USB? Is this SATA? Is this NVMe or maybe network? And PDS phase is about that. So TPM, probably most of you know this is Trusted Platform Module, and this is international standard created by Trusted Computing Group this is standard for secure crypto processors. Okay, so I believe this slide is very important to understand when we're talking secure boot. Typically, when we're talking secure boot, we think about multiple technologies. So on this slide, you can see that on the left we have some S-RTM or S-RTM, depending on the implementation. And we have typically this is held by AMD PSP, Intel ME, or some boot ROM, some part of SoC. And this piece is provisioned in manufacturing mode to verify signature in certain way. There are some, of course, problem with reowning and various other stuff with open tools for that, but this is maybe different story. And this component do the verification and execution and sometimes measurement of the further phases. And then it starts booting the computer. The first phase is SEC, then PEI, then Dixie, then BDS. Typically BDS jumps to bootloader, and then we're running some operating system. So to explain how the secure boot works, we have three kind of components. First technology that is used is silicon vendor security technology, which covers the S-RTM point, and typically it covers SEC and PEI phase because those components are not covered by the UEFI specification, UEFI secure boot specification. So then we have finishing the silicon vendor world, and somehow we have to jump into UEFI secure boot world. And this is the place where independent BIOS vendors or IBVs play the role, and they typically glue those two environments in their specific way. And then after that, we can say we have something which is specified in UEFI specification. It is UEFI Secure Boot. What kind of problem we have and what we have to achieve in this Secure Boot world to make things reasonably secure? First of all, it would be great if the S-RTM would be reasonably open. So there are some things that going on in the ecosystem that happened over last year, which is one of the things is LibreBMC. Of course, this is more related to server environment, but we hope that this project will evolve. And there are already discussion that it may evolve to laptop environment in form of environmental controller or some other thing, which may play a role of root of trust for verification. We will see. So that's interesting approach. Other thing is project of LPM Plant, my other company, which is called LPN TPM, which is more about open TPM, open source TPM with auditable code, with auditable hardware to some extent, because we probably will use off-the-shelf microcontrollers, but the software will be open and the schematics will be open for that, which this can help in opening the S-RTM part. Then it would be great if our system ROM, so our blue rectangle, will contain open source firmware. Of course, this is most of the market is not like that, and it would be great if it will not contain binary blobs. So even if we have sometimes open source firmware, core boot stuff, we sometimes have to rely on silicon vendor initialization code or some other components like for graphic stuff. Those are closed and we don't know what's going on. Ideal world would be if those components would be open, then this whole chain of secure boot technologies would be more transparent and we think it would be more secure thanks to that. And finally, we have our bootloaders, OSs, hypervisors, which every of these OSs and bootloaders use kind of other boot protocol, we can say, or at least, so for example, some bootloaders are created to unify boot protocol, some are created for supporting different boot protocols, and fragmentation in the bootloader OS hypervisor world and lack of compatibility in boot protocols between them kind of contribute to problems with implementation of correct continuation of chain of trust. How this is related to virtual machines? First of all, if we're looking at this chain, we have like similar situation. We're starting with some proprietary S-RTM, and then we're going to system ROM, and then we have bootloader, or we don't have bootloader. We may right now just run EFI application, which so for example we can run Zen EFI or Linux directly. But so let's consider bootloader as an optional thing here, and then we can start hypervisor. Then hypervisor starts VMs. It starts with DOM0 and then probably other VMs. So this is how this relates, because without correctly implemented static root of trust for measurement and verification, the verified measured boot of the VMs doesn't add anything to the security properties of the systems. So that's the point. Without correct boot chain and correctly verified and measured components before starting VMs, the security properties of the VMs are not the one which we would like to have. And the other thing which may help in fixing all this environment is just to ignore S-RTM and start to rely on DRTM, dynamic root of trust for measurement, which is like, as I said, the difference is that we're not doing this once at static point in time, but we're doing that dynamically at whatever point in time we want, and then we create another root of trust. This is very interesting concept. This is what Trenchboot project tries to do, but I will not go deep with that here. What we can say that the problems of the static root of trust for measurement and verification definitely leads us to conclusion that maybe this is not the correct approach, because it's very complex and the chain is very long and it is very hard to maintain its security properties. And on further slide, I would like to discuss progress of the development and approaching various problems in this boot chain, which happened over last year. So to sum that up, last year I presented S-RTM for Qubes OS VMs. You can watch that on YouTube. There was discussion after that, and there is great feedback from Andrew and Marek. I will discuss what key takeaways from that presentation were. Then in March 2021, Oliver from Vates, from XCP&G team, organized Zen Secure Boot and Lockdown working group meeting, where we kind of discussed what kind of problems we have and how we can attack it, and what we have to solve to make Zen even possible to maintain the security properties during the execution, assuming that secure boot, previously secure boot setup works correctly. Then on Zen Developers and Design Summit, Bobby, also from XCP&G team, gave presentation enabling UEFI secure boot on Zen. And there was also kind of design session from Igor Druzini from Citrix, and he discussed VTPM, which is partially related to measured boot, which of course it is interesting that the corporations are pushing in that direction, and I will explain why this happened. XCP&G provided secure boot for VMs. There is also work from Trammell Hudson. He informed about this on OS FW Slack, so open source firmware Slack, and this was related with safe boot, and he used software TPM. There are some things that are not directly related. I told you about LibreBMC, LPN, TPM, but I will not talk about that anymore in this presentation. So let's get back to 2020. In my presentation last year, I told you about various root of trust that we have, that Trusted Computing Group defined. What kind of practical use cases of those root of trust can be for virtual machines. Some design ideas, how we can work around the limitations, how we can introduce TPM through QEMU features. We discussed that as SWTPM has some interesting capabilities and can be used in various configurations. We can leverage it. There is also this outdated VTPM architecture in Zen. And also I presented how those things can be connected in kind of 3M Devs Dream Design, like as a concept, as a solution. So assumption and potential feature ideas for TPM usage in Qubes OS were discussed last year, and the key takeaways were as follows. If we want to build everything, we will not accomplish anything meaningful. We have to build some small pieces. That was comment from, if I recall correctly, from Andrew. And also there was discussion that there are significant difference between various types of VMs. So we have PV-HVM, PV-HVM, and so on and so on. And PVH seem to be the trend, seem to be the machines, and PVH do not use QEMU, but it use PV drivers. But it is possible to create emulation environment and hook into PVH VMs, and this emulation environment can be in QEMU. So definitely we can use this mechanism to deliver software TPM emulated in QEMU and expose its interfaces to PVH VM. And that's probably one of the decisions and trends that will happen. Also, during the review of the presentation, I believe Daniel or Rich pointed to virtualized trusted platform architecture specification from Trusted Computing Group. So there are some graphics here. I don't want to go very deep with that because it will take too much time. But you can see this is layered approach. At the lower layer 1, we have physical platform which contain physical TPM and physical root of trust for measurement. On top of that, we have a virtual machine manager, which is our hypervisor, and it maintains various components, like it maintains its attestation of itself, it maintains virtual platform migration engine, so we can migrate platforms we maintain. Then, of course, Virtual Platform Manager is responsible for handling and creating new VTPMs and virtual root of trust for measurement. And those components are used then by various guests, Windows guests, Linux guests. So this slide shows potential attestation flow. As a first step, we obtain VM integrity evidence from the guest OS VM, where this, of course, that guest OS VM got some attestation. Again, it obtains all the evidence from virtual root of trust for measurement and VTPM, which may be rooted in a physical environment. Then next step is verification of integrity evidence. Then we can obtain the same. So of course, this virtual machine operates in some hypervisor environment, and that's why we also would like to know what's the status of hypervisor, and that's why we're doing also deep attestation through VMM service, through hypervisor admin VM, we can say, and do the attestation of the hypervisor. And finally, we also verify that site, and if everything is okay, we assume we can deliver, for example, some secrets, or we can allow the VM to operate in certain way. So this is good food for thought, what kind of use cases were discussed in 2011 in Trusted Computing Group. Now I would like to discuss presentation from Bobby, which kind of presented what is Secure Boot, how it works, what kind of key hierarchies we use in UEFI Secure Boot, and then chain of trust in shim present systems, and how those can be used with Zen. Also various other configuration which Zen can leverage, in which Zen can leverage UEFI. And also there was discussion about some limitations. There was Microsoft CA mentions as a signing authority. So typical rumors are like typical situation about Microsoft CA as a signer of UEFI certificates is that Microsoft kind of dominated this environment, but this seemed to be not exactly the true, because some rumors say that simply nobody in UEFI forum was able to handle this problem and nobody wanted. And that's why Microsoft stepped out and took over that situation. But that's just a side note to the UEFI Secure Boot. So what kind of things Bobby presented in his presentation? So let's assume that the Secure Boot works. We have all the S-RTM components working. Then we finally jumping to something that we can control in most cases. And first configuration is based on shim and use only PE-COF file. So shim can verify only PE-COF. So in this situation, we're starting as a first stage bootloader shim, which install UEFI shim-log protocol, and then this shim-log protocol, and then shim verifies Zen, and then Zen can use shim-log protocol to verify all the further components in DOM0. So there are some minor problems here. It will work only with PE-COF file because that's what's supported by shim. It will not work with any legacy multi-boot 1-2 binaries. And that means, of course, that Zen will have to maintain multiple build targets, what is a problem, and we would like to avoid that. This configuration can also work with not unified and unified Zen EFI. Not unified means that the command line and params for starting hypervisor are not built into Zen FE. Other configuration which can be considered is not starting Zen EFI directly from shim, but use grab as an intermediate player. What this gives us? This gives us ability that grab contains something called verifier framework, and this verifier framework gives ability to use different signature schemes. So we don't only have to use UEFI X508, X509 certificates, but we can also use GNU-PG. So Verifier framework and first implementation of support for Zen Multiboot was done by Daniel Kieper and presented on Platform Security Summit in 2018. And these patches were picked by XCP-NG team. And yeah, there is ongoing discussion on Zen Devil how to address that and if it is even possible to get rid of multiple binaries for Zen. So what are the key takeaways? Based on Bobby email to Zen Devil, the key goal is to achieve Zen binary that can be verifiable with shim, the same binary. Can be booted on BIOS platform with grab2. It can be booted on EFI platforms with grab2 or EFI loader. So yeah, so that's something that will reduce the number of build targets, and of course like improve the ecosystem. But it's hard to address all the needs. Yeah. So and there is other important thing that Bobby highlighted. Linux and Zen suffer from the same issue, which is potential of using some of the advanced feature and debugging feature, tracing features to subvert the runtime security properties provided by previously well-set UEFI Secure Boot. So there are some advanced features, some debugging features that may just help in subverting the security properties that we achieved thanks to correctly booted hypervisor or correctly booted kernel. Linux kernel addressed that through Linux kernel lockdown effort and feature. And yeah, so that means that Linux kernel locks down some features, and even root cannot use those features. To avoid the situation that we lose security properties, there are various levels for that, and there is a link here if you are interested in that topic. So Zen lockdown have to be addressed, and the Linux kernel lockdown will be treated as a model solution. But the problem with Zen lockdown is that it will not fix all the issues, because the nature of DOM0 and its superpowers as a admin VM are also problematic, and we have to somehow take care of that. And Linux kernel lockdown will not finish all the problems, because DOM0 still is kind of admin VM and can subvert some security properties. This is quite complex, and yeah, so hopefully we can discuss that after the presentation. From open source firmware perspective, we think that Qubes OS and Zen project should think how to not break the firmware updating methods while implementing Zen lockdown, because this is easy to implement all the security lockdown mechanism, and then of course not being able to deliver firmware updates or rely on kind of SMM based updates, which is other problem. Of course, SMM is a attack vector, and we know about that, and we would like to avoid it as much as possible, because it's rather assuming proprietary IBV path of solving the firmware update problem. In terms of other discussions, there was a Igor presentation about reviving VTPM 2.0 architecture. And of course, this is motivated by some certification, this time from Microsoft. It's called Microsoft Server Virtualization Validation Program. It looks like they will require TPM 2.0 for Microsoft Server VMs, what means that the hypervisor have to somehow deliver that. Certification will start very soon, so I believe this effort of introducing virtual TPMs into hypervisor world will accelerate in coming months. If we can talk about other work delivered by XCP-NG team, First of all, Bobby gathered various patches and various tools that are needed for enabling secure boot in XCP-ng, and there is a GitHub repository for that. VMs, virtual machines which use OVMF, so UEFI package responsible for delivering firmware for virtual machines, can already use secure boot, and you can, if you can correctly go through setup menu, BIOS setup menu of that VM, you can do the provisioning, you can so you can deliver all the certificates, you can include Microsoft certificates, or if you don't want, you may just include your certificates. So everything from the UEFI specifications perspective is supported, and you can even compile OVMF with built-in certificates and just support what you need. So that's good thing. And there is discussion thread on GitHub issues of XCP-ng project. And of course, like big kudos to XCP-ng team for picking that up and moving that topics forward. In case of meeting that happened in March 2021, which gathered quite big crowd, there were many organizations, many individuals there discussing secure boot and lockdown. Key accomplishment of that meeting was to gather requirements for Zen lockdown. Linux lockdown basic stuff seemed to work fine with Qubes OS. Marek mentioned that there were some minimal tests to look into that. Probably we can talk more about that after this presentation. And we narrowed down some work items that have to be done for Zen lockdown. So one of the things we have to look into is live patching, kexec, priv command, PCI pass-through, QEMU, but PVH probably will eliminate or reduce that, and also how we want to protect command line and which things are secure, which are not secure. This is like wider discussion and more complex thing. In terms of open source firmware Slack and Tramel's work, Tramel and couple other people work with SWTPM, kexec, and SafeBoot. They proved to run couple scenarios. And why is this important? It is important because FWTPM is best candidate for serving as a virtual TPM or to deliver virtual TPM properties. Of course, in long run, we would like to be rooted in hardware, but this is complicated stuff. We have just this VTPM architecture, which is already outdated. But getting back to what Tramel and others did, they did testing in QEMU with core boot and heads, and they emulated as SWTPM to prove provisioning of heads works fine. They also proved that with OVMF, so with UEFI environment. They did attestation in above cases, so that's very good. So they use SafeBoot for attestation. They kexed Windows, and they saw how Windows interacts with TPM, and they added this support in SafeBoot. So yeah, so that proves that SVOOT TPM is good project, healthy project, can be used in various scenarios, various interesting scenarios, and we should look at that and maybe adopt that in the virtual machine environment. Yes. So to finalize this talk, so first of all, we have many different problems in many areas. We have Zen lockdown problem. We have secure boot, working secure boot problem and the complexity of it. So it's not. It will definitely take time to enable all necessary component, but it is interesting that some of these concepts are on corporate agenda, and there are resources that will push that forward, and that's good. There is this collaboration or even support from bigger organizations. So there are resources. There are some resources to move that forward. Of course, we would be glad to see to make it faster, but it's not always the case. Verified boot, including UEFI, have a lot of needs, and this is something that we're talking from open source firmware consulting company perspective, we would be glad to have more open hardware for root of trust. I believe RISC-V is one of the way to solve that, or there may be other open ISA which address that. There's problem with correct implement, even with the current configurations, there is problem with correctly implemented chain of trust, because there are bugs in either independent BIOS vendors code, either there are tools which are not available for provisioning, which is next case. There are many problems here, yeah. Despite verified boot for VMs does not need those properties, but still we have to rely on the previous components in boot process. So yeah, previous components have to be secured in correct way. That's why we need good tools for provisioning, Intel Boot Guard, hardware validated boot, and other hardware security mechanisms. And finally, covering hypervisor and DOM 0 with verified boot is also challenging, and that's where Linux Zen lockdown going. That's where Linux lockdown mechanism may help a little bit, and then yeah. So we have to think if what's the best for the VMs, and shall we use UEFI Secure Boot? Maybe there is a way to use Core Boot, vboot for VMs, and I already saw that as a solution in some cases. So yeah, so there are many challenging problems to be solved as a part of the S-RTM and Secure Boot introduction to the virtual machine ecosystem. Okay, and that's it. Thank you very much, and I'm waiting for your questions.